In today's statistics lesson, we will be discussing measures of position. Please feel free to press pause and read through today's objectives. All right, our first measure of position that we are going to discuss are called quartiles. Now, quartiles are part of a larger group called fractiles. Fractiles are just when you take your data and you partition it or divide it into a certain number of equal parts. So 5 parts, 6 parts, 7 parts, however many parts you want. The most popular ones are deciles. So you cut the data into 10 equal parts. Percentiles, where you divide into 100 equal parts. And quartiles, where you divide into 4 equal parts. And when we talk about quartiles, we're going to break quartiles down by each specific quartile. So the first quartile, which we call Q1, is the lower half, the lower 1/4 of the data. Not the lower half, it's the median of the lower half. Quartiles are great because they're based on medians. The second quartile itself is the median of the data. The first quartile is the median of the first half of the data. And the third quartile is the median of the second half or the upper half of the data. So quartiles, I think, are quite useful simply because they use medians and very easy to work with. So let's talk about them. All right, so you are given a data set about the amount of fuel that automobile commuters waste due to traffic congestion in the 15 largest urban areas. So the data is listed not in order first, and then I put it in order for you just to make it nicer. So the italicized one is the one that's in order. Okay, it says find the first, second, and third quartiles of this data set. So the first thing I find is Q2 because that divides the data in half. So there are 15, so that means there will be 1 in the middle because it's an odd. So there would be 7 on the bottom half. 1, 2, 3, 4, 5, 6, 7. This would be our Q2, and then there should be 1, 2, 3, 4, 5, 6, 7 on the top half. So that is my Q2. It's the median of all of the data. And then I can go through and find the Q1, which is the median of the bottom half of the data. So of this half, there are 7 data points now. So that means there will be 1 in the middle, and it'll be this one right here. That is my Q1. Notice there are 3 below and 3 above. And then you can also find your Q3, which is the median of the upper half of the data. So you've got 7, so you've got 1, 2, 3, and this right here would be my Q3. So Q1, median of the lower half, Q2, median of all the data, Q3, median of the upper half of the data. Oh, I should go back and explain a little bit more about what that means. Let me go back to my slide. Okay, so what does that mean? So 50% Q2 is our median. That is 50% is above and 50% is below. The Q1 means that this is 25% of my data. This is 25%. This is 25%. And this is 25%. So notice it cuts it into 4 equal pieces. So about 25% wasted 26 gallons or less. Half of the cities wasted 31 gallons or less, and 75% wasted 35 gallons or less. And then 25% wasted more than 35 gallons. So it's a nice way to cut it up into nice equal pieces that you can talk about. All right, so same thing here. If you'd like to try this example, go ahead and press pause and give it a try. All right, welcome back. So in this data, it is in order. It was nice that I put it in order for you. But notice the middle one, because there are 25, that means there is going to be 1 in the middle because my n is odd. So there should be 12. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. So this right here, that would be my Q2. Your Q1, you would have 12 on the bottom, which means it's an even number, so you won't have 1 exactly. So 1, 2, 3, 4, 5, 6. So these 2 are the middle, which means that Q1 would equal 47, right? Add those 2 up, divide by 2. And then same thing up here, 1, 2, 3, 4, 5, 6. 2 in the middle. So there's my Q3. Which would be 58.5. Again, add those 2, divide by 2. You can also use technology to find quartiles as well. So if you have the opportunity to use technology, and this is a great way to check to see if you did everything right. And again, just depending on which technology you use, it will give you your quartiles. It just won't list Q2, it'll just say median. So just know that Q2 is median. And then you can match that data. Notice we have exactly the same data that Minitab got. TI-84 Plus gave us the same thing. StatCrunch gave us the same thing. StatCrunch did round, so keep that in mind. It might be slightly different, just depending on how the computer is programmed to do it, but you should get about or very close to the same answers that we got. All right, another very useful tool when we're talking about the variation of data is the interquartile range, and that gives you the range of the middle portion, so the middle half of the data, and that's just the difference between Q3 and Q1, right? Your interquartile range. Inter meaning inside, so it makes sense. It's the inside half of the data. It's a range. Obviously, take the maximum minus the minimum, Q3 minus Q1, and that will help you. You're going to need this to find outliers later on, so it's a nice thing to have. So if you are going to find an outlier and define it, this is how you define an outlier. First, you have to find all your quartiles, obviously. Step 2, find your interquartile range. And then whatever that interquartile range is, you're going to multiply it by 1/2, not 1.5. You're going to take that number, whatever that is, and subtract it from Q1, and then add it to Q3. Anything below the Q1 minus that 1.5 times the IQR will be an outlier, and anything above the Q3 plus 1.5 times the IQR will also be an outlier. So you could have outliers on the low end, you could have them on the high end. All right, so if we take that previous example and we look at finding any outliers. So again, remember from the first one, Q1 was 40, the one we just did, Q1 was 47 and Q3 was 58.5. All right, so first we have to find our IQR, which is 58.5 minus 47, and that's going to give us 11.5. You're going to take that 11.5 and you're going to multiply it by 1.5. Okay, and that's important. You're going to need that number, okay? Because when you want to find the outliers on the low end, you're going to take the Q1, which is 47, and you're going to subtract that 1.5 times that 11.5. And that's going to give you your low end. That turns out to be 29.75. So anything below 29.75 will be an outlier. And then, let's see, and then you're going to take Q3, which is 58.5, and you're going to add that 1.5 times 11.5. And that is going to give you 75.75. And anything above that will be an outlier. So in this case, there's only one entry that was an outlier, and that was the $19,000 tuition. So 19,000 is an outlier, but none of the other ones were outliers. So that college that only charges $19,000 would be considered very cheap compared to other colleges. All right, what else can we use these quartiles for? Another thing that we can use them for is to create what we call a box and whisker plot. And this is a great data analysis tool, and if you go into the actuarial sciences, you will use this. It highlights a lot of important features of your data set very quickly. You can compare lots of data sets side by side using these, which is also very useful. And all you need to know is that what we call the 5-number summary. You need to know the minimum, the Q1, the median, the Q3, and the maximum of the data. If you know these things, you can draw a box and whisker plot. So first find your 5-number summary, and then on a number line. That's all. Box and whisker plots are just on a number line. You're going to create your number line, and you're going to plot those 5 numbers that you found on that scale. And you're going to draw a box around the Q1 and Q3 with a vertical line representing Q2. So you get that box in blue in the middle, and then just do a whisker on each side from Q3 to the max and from Q1 to the minimum. And then you've got your box and whisker plot. Again, remember, math people, we're not creative. We just name stuff what it looks like. All right, so let's take a moment and create a box and whisker plot. All right, so our minimum was 19. So at 19, we're going to put a dot. Our Q1 is 47, so at 47, we're going to put a line. At 55, we're going to put a line. At 58.5, we're going to put a line, which is about right there. And at 61, we're going to put a dot for our max. So here's our box, and here's our whiskers. So we know that each portion of this is 25% of the data. So this is 25%, this is 25%, this is 25%, and this is 25%. So notice how the top half is very, very compact. There's not a lot of variation in the top half, but in the bottom half, there's a lot of variation going on, especially that bottom 25%. So we can talk a lot about how that works. We can also do what's called a modified box and whisker plot. And I'm going to do that in red. So notice that we had 19 was an outlier, and we talked about that in the previous example. So I would just put a little asterisk here at 19 instead of having the whisker be that long, and then put a dot for the minimum, which is the last data point that wasn't considered an outlier. And I think that was 30. So I put a dot here at 30, so that would be my whisker at the bottom. So with that slight modification, it really shows you that 19 was a huge outlier compared to the bulk of the data. So that's just what they would call a modified box and whisker plot. So you may see them either way, as the traditional or as the modified version with the outliers shown. Other measures of position we can use are percentiles and fractiles. So we've got our deciles, and our percentiles are probably the most common. And percentiles are probably used the most just because they use them from everything from comparing your test scores on SATs and ACTs, and they use them for talking about when you're a kid, when you go to the pediatrician, they talk about your height and weight and what percentile you're in compared to all the other kids. So you've probably seen percentiles more often than deciles. So here is an ogive that represents the cumulative frequency distribution for SAT results. So if your test score is in the 90th percentile, you would go to the 90th percentile over here, you would go to your ogive, and then just come down here and tell me what that score represents. So that score looks like it's about 1350. So if you have a score of 1350, that means that you have scored better than 90% of the students who took the SAT. So 90% of students had a score of 1350 or less on the SAT. So lots of different ways that you could, talk about it, but that's basically how it works. All right, so same graph. This time I'd like you to tell me what score represents the 40th percentile. All right, so you go over here to your 40th percentile, you're going to go to your graph and then go down. And notice it looks like it's about 1,000. So if you have a score of 1,000, you only scored better than 40% of the people. That means 60% did better than you did and 40% did worse than you did. So that's kind of how percentiles work, which honestly I kind of like. All right, but if you are given a data set and they want you to find what data set from your data set, which entry corresponds to that specific percentile, what you have to do is that the percentile of X is going to be equal to the number of data entries less than you. So you're the X divided by the total number of data entries times 100. So that is the formula you would use to find it. So let's do an example and then we can walk our way through it. So let's say, again, here we're back to our tuition data. Okay, we want to find the percentile that corresponds to 57. All right, so we're going to use that 57th percentile, and that is called P sub 57. That's how they write it shorthand, percentile 57th. Okay, that is going to be the number of data entries below you so below 57, divided by the total number. All right, so if you look on here, here's 57. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I've got 15 people below me, and we had 25 total schools that we got data from. So, and then multiply that by 100. So put that in my calculator, and I get 60th. I had this backwards. This is what we're trying to find. We're trying to find the percentile. So scratch that out. We're supposed to find the percentile. So we are in the 60th percentile. So P sub 60, sorry, didn't mean to get that wrong. All right, so again, number of data points below you, and that's very important. A lot of students forget that they have to be the number of data points below you, not including you, below you. All right, so say we have the Space Mountain wait times from Disney World, and we want to find the 25th percentile. Now, we could use the formula. That would not be horrible, right? We know that we are the 25th percentile. That means the number below us divided by the 50 that they gave us times 100. So I could use my formula and just kind of work backwards. So 50 goes into 100 twice. So 25 equals 2 times the number below me. So divide that both sides, and I get 12.5. So 12.5 is the number that are below me. But obviously, you can't have a half of a data point below you, right? So if you get that, you would change that to 13, right? Round it to 13. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that one is the one below us, this one right here. So that means I am this guy right here. So 25 minutes is my wait time. That's my 25th percentile. That means 25% of the people have been waiting less than 25 minutes, which that's not too bad. All right, you could also, because this is the 25th percentile, the 25th percentile is the same as Q1, right? Because they do by quarters, 25. So if you wanted to, you could also find that 25 by just finding the median of the lower half. And you should also get 25 as well. So you have options when it comes to some of these percentiles if you recognize that they are maybe a quartile. But something like this, where you want to find the 65th percentile, obviously that's not a quartile, so I'd have to do it the old-fashioned way. All right, so the 65th percentile is going to be the number below me divided by 50 times 100. Right, so 50 goes into 100 twice, and then I would divide both sides by 2. So I've got the number below me is going to end up being 32.5, which obviously can't be, so we're going to round that up to the 33rd spot. So 10, 20, 30, 31, 32, 33. So that means I would be this guy right there. So the 65th percentile is going to be 40 minutes. Again, a very simple process, but a lot of students forget that it has to be the number below you. All right, but the one that we are probably going to use the most in this class is something called the Z-score. And this is sometimes called the standard score. Z-scores are used to represent how many standard deviations you are away from the mean. That tells you your position compared to the mean. And this one is going to be most useful, and you're going to see this throughout the later chapters that in the later lessons that we discuss. All right, it's a very simple formula. Z equals the value minus the mean divided by the standard deviation. And that Z-score will always go to 2 decimal places, just to let you know. So you might want to make a note, 2 decimal places. All right, and there's a reason for that, and we'll talk about that in later lessons. All right, so the mean speed of vehicles driving along a stretch of highway is 56 miles per hour with a standard deviation of 4. You measure the speeds of 3 cars that are traveling along this stretch of the highway. One's traveling at 62, one's traveling at 47, and one's traveling at 56. Find the z-score that corresponds to each speed. All right, so we have a speed of 62, we have a speed of 47, and we have a speed of 56. So we're going to find the z-score for each. So z, remember, equals score minus mean over standard deviation. So 62 minus the mean, which was 56, and again, you might want to like highlight that or make a note, and then your standard deviation, right? Here's your standard deviation, is 4. So when you put that in, that one comes out to exactly 1.5. So that means the person traveling at 62 miles an hour is 1.5 standard deviations above the mean. That's what that means. Positive, so you're above. All right, let's try 47. Let's find his z-score. So 47 minus 56 over 4. And that gives us a z-score of negative 2.25. So that person is going 2.25 standard deviations below the mean. That's probably the driver we're all yelling at. All right, and the last driver, 56, so 56 minus the mean over 4. Well, 0 divided by 4 is still 0. So that means that person is traveling the mean speed for that stretch of highway. All right, so notice z-score is not difficult to find, and then it just gives us an idea of where they are compared to the mean, which is rather nice and will come in very handy in later lessons. All right, z-scores also come in really handy when you want to compare two things that aren't alike. Like if you want to compare your SAT score versus your ACT score, they're completely different tests using completely different scales. So you could find their z-scores and then compare them, which is rather nice. All right, in this case, we're going to compare men's heights and women's heights. So there is the mean and standard deviation for both men and women. So it says compare the z-scores for a 6-foot-tall man and a 6-foot-tall woman. All right, so in both cases, X is going to be 6 feet is 70 inches, right? So 72 inches. So that's what we're looking at in each case. But we have to do the men first, and then we have to do the women. So let's do the men. All right, so my 72 minus the mean divided by 3.0, which is my standard deviation. And that gives me a z-score of about 0.7. So a man who is 6 feet tall is not quite 1 standard deviation above the mean. So he's taller than the mean, the average man, but not too tall. Now let's talk about women. Okay, same thing. If I have a woman who's 6 feet tall, so 72 minus 64.3 divided by 2.6. And that turns out to be 3.0. So a woman who's 6 feet tall is 3 standard deviations above the mean. She is very tall for a woman. So notice how having that basis, we can compare men and women. Obviously, men are taller than women on average. So important to have that information. And then you might ask yourself, 3 standard deviations is way, that's really far away, right? We're talking about, if you think about that empirical rule we talked about before, right? 3 standard deviations, within 3 standard deviations, we had 99% at 7% of the data. So that means that this woman is extremely tall. So she is very unusual for a woman to be 6 foot tall. That is out of the ordinary. But for the 6 foot tall man, this is normal, right? They're not even 1 standard deviation above the mean. So they're very close to the mean. So that's another thing that we can use standard deviations and z-scores to help us with, is how unusual are these? All right, so I have 2 examples, and then I would like you to tell me which one is more extreme. So we have our first example, which is a adult that has a temperature of 99 degrees, and they gave you the mean and the standard deviation for those adults. And I'd like you to compare that to a quarter that has a weight of 5.7790 grams. And again, they gave you sample data with the mean and the standard deviation to help you. So press pause and give these a try and find the z-score for each. All right, so let's do the first one. So the z-score for the temperature is 99 minus 98.2 divided by 0.62. And that turns out to be about 1.29. So it's more than one standard deviation above the mean, but not unusual. So that's interesting. Now let's do the quarter. So the quarter is 5.7790. We're going to subtract the mean, which is 5.63930, and divide it by the standard deviation, which was 0.06194. Put that on my calculator, and that's about 2.26. So that quarter is about 2.25 standard deviations above the mean. So notice in this case that the z-score is much higher for the quarter than it is for the temperature. And it doesn't matter what direction it goes in, it just is how far is it from the mean. And so in this case, the quarter is the more extreme case, right? The more extreme case would be the quarter, because its z-score is farther from the mean than it was for the temperature. All right, so hopefully this gives you some ideas of how you can talk about your data and their position compared to other data points. Please make sure you come back next time. We'll talk some more. See you then.